Welcome, teachers. We are working in section 1.1. This is part 2 of a video discussing an introduction to problem solving. I want to remind you that there's two things we have going over here. We talked about the 4-step method for problem solving, and then we want some techniques for solving problems. In part 1 of the video, we talked about the Gauss problem. In part 2, we're going to talk about some other types of problems, but let me remind you about the 4-step method. Step 1, understanding the problem. You want to make sure you clearly understand what's going on in the problem. 2, we're going to devise a plan to solve the problem. 3, we're going to carry out the plan. And 4, we're going to make sure it worked and see if we can generalize that for different types of problems. Now, one thing we mentioned in the first video are different types of strategies. And of course, you use different strategies for different problems, and your strategy could be different than my strategy, and we might even use more than one strategy to solve a problem. But I want to remind you, looking at a simpler case of a problem is often a good way to go. Another method for solving a problem is making a table. An often used strategy in elementary school mathematics is making a table. A table can be used to look for patterns that emerge in the problem, which in turn can lead to a solution. So if you feel kind of overwhelmed by your problem, see if you can organize the information and glean a pattern from it. Okay, now we're going to start a brand new problem. I'm going to go ahead and warn you, this problem is not easy either. It's as similar to dealing with the Gauss problem. We've really got to break down what we're doing. Okay, and here it is. We're going to arrange the numbers 1 through 9 into a square. Okay, that looks like this. It's subdivided into 9 smaller squares like the one shown in the figure. Now here's the trick. The sum of every row, which is across left to right, the sum of every column, which is up and down, and even the diagonals all add to the same number. Wow, right? That's a lot. We've got to see if we can come up with a plan to do this. So let's just think this through. Let's just play around. Say we make this first number right here, let's just say a 1. And we make this a 5. Then what do we need to make this to total? We don't even know what it needs to total, do we? Let's just say it has to total to be 9, right? So if this were to total to be 9, if this is a 1 and this is a 5, that's already 6. Then we need a 3 here to make that total a 9. Now, we've already used the 1, the 5, and the 3. So I can't use a 1, a 5, or a 3 anymore, except in the places they're in. And if this is 9, then this row would also have to be 9. So we haven't used a 2. Okay, so 1 and 2. 1 plus 2 is 3. 3 plus 6. Hey, we haven't used a 6. That would total to be 9 also, wouldn't it? Okay. Now let's check our diagonal. Since we already have two numbers, 3 and 6, what would need to go here to make the diagonal total to be a 9? Well, it already adds to be 9, right? So we would have to put a 0 there, but a 0 is not allowed. So it looks like we've already messed up. But we messed up kind of big time because we don't even know what these things are supposed to add to. But the reason I discussed this is I wanted to make sure you understood the problem. And you do, right? We're trying to fill 1 through 9 into all these squares. We're not going to reuse any of those numbers. And each row, each column, each diagonal has got to add to be the same number. Not necessarily 9. We don't even know what that number is. Now remember, step 1 is to understand the problem. And I feel like we did that in the last page, right? Each of the 9 numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, must be placed in the cells, which are these little squares, a different number in each cell, so that the sums of the numbers in each row, each column, and each diagonal are the same. And they call it the major diagonal, because you could make little minor diagonals right here, but they mean the 3 this way and 3 this way. But here's the deal. We don't even know what they need to add to yet. So that might be what we call a sub-goal. So keep that in mind. if we knew the fixed sum of the numbers in each row, column, and diagonal, we would have a better idea of which numbers can appear together in a single row, column, or diagonal. So our sub-goal is to find that fixed sum. How are we going to do that? How do we know what needs to be the total of each row, column, and diagonal? Well, the sum of the 9 numbers, 1 through 9, equals 3 times the sum in one row. Why would that be? Okay, well, you use 3 of the numbers, right? So for each row or each column, each diagonal, you're using 3 of the numbers. So that's why the sum of 1 through 9 is 3 times the sum of one row. So let's add 1 through 9. You can do that in a calculator. 1 plus 2 plus 3 plus 4. Hey, we could even use Gauss's trick to do that too, couldn't we? But I've saved you a minute. If you add 1 through 9 in your calculator, you get 45, and then 45 divided by 3 is 15. So what we've learned here is that each row, each column, and the 2 major diagonals have to sum to be 15. Okay, now we're still in the devising a plan stage, right? We know they sum to 15. You could just play around and put numbers 1 through 9 in your squares, trying really hard to make sure each row, each column adds to be 15, and just move things around as needed. And that's called trial and error, or guess and check. You might find that you want to pull your hair out by the end of that. So I don't advise guessing and checking here because there's just too much guessing that you could do, and it could get frustrating. So we're going to devise a different plan. We need to decide what numbers could occupy the various squares. Well, we know that, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. You don't repeat any of them. But the number in the center space will appear in 4 sums, each adding to 15, 2 diagonals, the second row and the second column. Wow, wait, what? Okay, so let's talk about this. I'm just going to draw a quick, I'm going to attempt to draw a quick version. Not pretty, like what we're dealing with, right? Now, what they're referring to here is that this number right here, notice that it shows up in this calculation adding down, and this calculation adding it across, and this calculation on the major diagonal, and on the other major diagonal. Notice that's 1, 2, 3, 4 different sums. And that's what they mean. It'll appear in 4 sums, each adding to 15. So if we could figure out what number goes into this highlighted aqua spot right here, we'd be doing really well. Okay? Now what we want to do is make a list of all the possibilities of adding our numbers to get 15 and see which number shows up the most frequently. Doesn't that sound reasonable? So you could take your time, and this takes a while, to list all the possibilities of numbers 1 through 9 that add to be 15. And keeping that organized can be a little bit of a challenge, but just play around with it and see what you get. Okay? It says each number in the corners will appear in 3 of the sums. Okay, so let's go back and see what we're talking about here. So again, I'm back to my magic square here. It's not magic yet. I haven't put anything in it. But it's saying each of the numbers in the corner will be in 3 different sums. Is that true? So it'll be in that column. It'll be in that row. Hey, it'll also be in that diagonal. So after we find the center number, how about we see what other numbers are popping up pretty frequently, and those could be our corner numbers, right? All right, so let's keep going with this. We're feeling it. We're developing a plan. If we write 15 as a sum of 3 different numbers, 1 through 9, in every possible way, remember I mentioned that earlier, we could then count how many sums contain each of the numbers 1 through 9. Okay? Now, I want you to stop the video and take a minute and just start writing down all the possibilities of adding to be 15, right? So how would you do that? I would start with the biggest number, so maybe 9 plus, and you can't add 9 plus 8, right? That won't give you 15. 9 plus 7 is already too big. 9 plus 6 already adds to be 15. So how about 9 plus 5 plus, and that's already 14, I'm sorry, plus 1 would give us 15, right? Then you could do 9 plus 4 plus 2. Keep moving that over there. Then 9 plus 3 plus 3. That won't work, right? Because you can't do that. So that one's out. 9 plus 2. That's already 11. Plus 4, but we've already got that listed. You see where I'm going with this? You want to do it every way possible. You want to find a way to organize all that information. Now, I've already done that, so you might want to pause and do that, and then come back and meet me and see if we're on the same page. Now notice, if we do this, the numbers that appear in at least 4 sums are candidates for placement in the center square, whereas the numbers that appear in at least 3 sums are good for the corners, right? So look at your list. Do you see anybody that shows up frequently or the most? That should be our center square. And then the next most may be in the corners. Now let's look at the list. Let's see if our lists match. So I've got 9 plus 5 plus 1, 9 plus 4 plus 2, 8 plus 6 plus 1, 8 plus 5 plus 2. Notice I don't have any repeats. Like if you change the order, that's not going to get you there, right? Check it out. 5. Look, the number 5 shows up in more of the sums than any of the others. What does that mean? That means 5 needs to be in the center. Okay? Now, what else shows up a lot? Well, let's just look at our numbers one at a time. Like 1. Look at the number 1. 1 showed up right here and right here. I only see it twice. Okay. Look at 2. So there's 1, 2, 3. Seeing it 3 times. Let's look at 3. I see 1, 2. Let's just make a list, right? Maybe a table. So again, how many times did 1 show up? A pen. Here we go. How many times does 1 show up? 2 show up. 3 show up. 4 show up. 5 show up. 6, 7, 8, 9. Let's check this out. So 1. I just see it twice. Don't y'all think? Showed up twice. 2 showed up 1, 2, 3 times. 3 showed up 1, 2 times. How many times does 4 show up? 1, 2, 3 times. 5. How many times did we already established that, right? It showed up 1, 2, 3, 4 times. 6. There's 1 6, 2 6. Hey, there's 3 6s. 7 twice. 8. 1, 2, 3. 9. 1, 2, 2. All right, so how did this help? Let's highlight, right? Now 5. Remember, 5 was our winner because it showed up 4 times. That means 5 needs to go into the center. But what showed up the next number of times? Well, let's check out our 3s, right? So 2, and I need to get rid of this. 2 showed up 3 times. What other number showed up 3 times? 4 showed up 3 times. Okay. 6 showed up 3 times. And then 8 showed up 3 times. Let's let those be our corners. Okay, so the only number that appears in 4 sums is 5, so 5 must be in the center. And then we found out what needs to go in the corner. Okay, because 2, 4, 6, and 8 appear 3 times each. They must go in the corner. So notice what we did. We put 5 in the center, and 2, 4, 6, and 8. You can pick any corners you want those to go in, by the way, and just play around with it. Okay, if you choose 2 for the upper corner, then 8 must be in the lower right corner. Why do we know this? So if you randomly pick 2 of those 4 numbers to go up here, you've already got a 5. 2 plus 5 is 7. That means that must be an 8 that goes over there. And then you could just pick 6 to go over here, right? And then 6 and 5 is already 11, which means 4 goes over here. See how this works? And then you see what the last missing spots are and plug those in. Now, try to reproduce that on your own. Make sure you fill that in and you can see how that happened. So it says 6 in the lower left. They didn't put 6 in the lower left corner. Or upper right, that's where they put it right. And then complete the magic square. So very interesting, right? Let's look back. Okay, we have seen that 5 was the only number among the given numbers that could appear in the center. However, we had various choices for a corner, and so it seems that the magic square we found is not the only one possible. It means the solution is not unique. So there's other ways to do it, but very similar. Play around. Set it up another way. Move those corners around and see what happens. Okay? All right, now we got a new problem. It's about Bev and Jim. They ran a 50-meter race 3 times. The speed of the runners did not vary. In the first race, Jim was at the 45-meter mark when Bev crossed the finish line. So can you picture this? Bev finished, and Jim was right behind her 45 meters. Okay? That's in the first race. In the second race, Jim started 5 meters ahead of Bev, who lined up at the starting line. In that case, who won the race, do you think? We need a way of thinking about this, don't we? And then question B, in the third race, Jim started at the starting line, and Bev started 5 meters behind him. Who will win the race in this situation? So an interesting setup. We want to make sure we understand the problem, and I think you probably do, but let's look at it. It says when Bev and Jim run a 50-meter race, Bev wins by 5 meters, right? Because she was at the finish line and Jim was at the 45-meter mark. So whenever Bev covers 50 meters, Jim covers 45. That's very important. Bev covers 50 meters, Jim covers 45 meters. Now if Bev starts at the starting line and Jim is given a 5-meter head start, we are to determine who will win the race. Now let's just think about this. And you know what? A diagram might be the way to go. Okay, so 50-meter race. Here we go. There's our race right there. 50 meters. Okay. Now, right here, that's what Bev runs, right? In the second situation, she's running the whole 50 meters, but Jim gets to start 5 meters in. So how far does he run? Well, he runs 45 meters. So whenever Bev covers 50 miles, Jim covers 45 only. So if they cover 50 and 45 in the same amount of time, guess what? These folks are going to finish at the same time. It's going to be a tie, right? That makes pretty good sense. Here's a picture, a more accurate depiction, right? This is race 1, by the way. This is where we started this story. That Bev ran 50 meters in the same amount of time that Jim ran 45. And of course he was short. Bev was definitely the winner of the first race. But what about race 2? And that's the picture we just drew, race 2. So Bev runs the whole race again. Jim runs 45 meters in the same amount of time Bev runs 50 meters. But he got a 5-meter head start, which means they finish at exactly the same time. Come on now. There's Bev, there's Jim, exactly the same time. It's a tie. All right? But what about the third race? We got to think about that. Okay? Let's draw a picture for the third race. Now remember, on the third race, Bev, so here's the start line, right? And Jim is running a regular 50-meter race. He's at the start line. But Bev starts 5 meters before Jim. So if we think about that on our picture, so this is the normal beginning. This is where Jim starts, but Bev starts back here 5 meters. Okay? And again, Bev can run 50 meters in the same amount of time Jim runs 45 meters. So notice they both have 5 meters to go here. They're even right here at the 45 meter mark. Matter of fact, it says it right there. They will be tied at 45 meters. Because again, Bev ran 50 meters in the same amount of time Jim ran 45. So they're set up. Now, at the end here, who's going to finish first? Is it going to be a tie? Is it going to be Jim? Is it going to be Bev? Well, remember, Bev runs faster than Jim, right? Because Bev can run 50 meters at the same time Jim can run 45. That means Bev can run 5 meters faster than Jim can run 5 meters. Am I right? So Bev is the winner for this one. I think the picture helps a lot, though. Okay? The strategy there was just a diagram. Remember, this is a recap. We carried out the plan. Race 1, Bev wins by 5 meters. We knew that, right? Because she ran 50 meters in the same amount of time Jim ran 45. Race 2, they reached the finish line at the same time. Again, because Jim can run 45 meters in the same amount of time Bev can run 50, and he got a 5 meter head start. And then finally, race 3, since Bev is faster than Jim, Bev will cover that last 5 meters faster than Jim will, and then she will win the race. Looking back, the diagram showed the solution makes sense and is appropriate. A diagram sometimes is plenty to make sure you see what's going on. Here's another strategy. What about working backwards? In some problems, it's easier to start with the result and to work backwards. Remember at the beginning of the first video, I discussed we've all done it, right? We didn't know how to do a math problem and the homework, and you flip to the back of the book just to see what the answer is because it's an odd problem and you have to work backwards to get to that answer. But you learn a lot from that. And some word problems, even if you don't have the answer, working backwards can be a strategy. And we've got a problem right here. So it took workers 5 weeks to dig a 10-mile tunnel. Okay, 5 weeks to dig 10 miles. During the 4th week, the workers dug 2.5 miles. The next week, they dug 1.25 miles, okay, to complete the tunnel. How much had the workers completed after the first 3 weeks? So again, if you think about it, if you think about, you've got week 1, week 2, week 3, you can look at it like that. It says during the 4th week, they dug 2.5 miles. Y'all, I just can't get my pen to work. 4th week, 2.5 miles. The next week, that's the 5th week right there. And if we know the 4th week and the 5th week, can we not just subtract that from the 10 miles to get what was dug in the 3rd week? And that's all there is to this. This was not crazy hard like the other ones, y'all. This is just working backwards. So if we can calculate 10 minus the 2.5 from the 5th week minus the 1 and the 4th from the 4th week. Oh, I said that backwards. 2.5 is from the 4th week. 1.25 is from the 5th week. That is going to be our answer for the 3 weeks, right? So the workers completed a 10-mile tunnel in 5 weeks. During week 4, they dug 2.5 miles. During week 5, they dug 1.25 mile. We need to find how many miles of the tunnel they dug in the first 3 weeks. Again, let's subtract. Okay? We need to know how many miles they dug in the last 2 weeks, so we'll work backwards. In weeks 4 and 5, they dug 2.25 plus 1.25. Everybody's comfortable with that's 3.25, right? Or 3 3/4. I didn't even say that right. Do we know how to do that? Now, don't worry. We have a section coming up with fractions where we need to do this in detail. But just in case you're struggling with these calculations, we cannot add these mixed numbers until we have a common denominator, right? And we have a 2 and a 4. The common denominator there is 4. So I'm going to multiply this first fraction by 2 over 2. That's going to give me 2 2/4 plus 1 1/4. Now the rule for adding mixed numbers is to add the fraction parts together. Okay, so 2/4 plus 1/4 is 3/4. And 2 plus 1, the whole number part, is 3. So what they've built already that we know of is 3 3/4. Now we're going to subtract 10 minus 3 3/4. Now again, in a future section, we're going to cover in detail about how to do this. But in case you're struggling right now, we need to do 10 minus 3 3/4. Well, notice I have nowhere to subtract the 3/4 from. So here's what I'm going to do. I'm going to borrow from this 10 and make that a 9. I'm borrowing 1, but how do I write 1 with a base or a denominator of 4? Well, it'd be 4/4, right? 4/4 is 1. So 10 is equivalent to 9 4/4. And now I subtract 4/4 minus 3/4 is 1/4. And then 9 minus 3 is 6. So that's where that 6 1/4 comes from. So in the first 3 weeks, they dug 6 1/4 miles. Be sure to always use units. Really, I should have wrote miles here as well. It's very important that both you and your students are very comfortable with units. A number by itself really does not mean anything. It's talking about some sort of measurement. And so you want to indicate what that is if you know. Now let's take a look back. The answers make sense because 6 1/4, remember that's for the first 3 weeks, plus 2 1/2, plus 1 1/4 does equal 10 miles. Now again, the real way to do this, and we're going to break this down into a lot of detail when you jump into the fractions section about how to do this, but you need a common denominator so you can add those 3 fractions together, and then you'll add the whole number parts together also, and then you'll have to simplify that fraction to get the 10 miles. If you're worried about fractions, go ahead and take a minute, pause it, and work that out yourself to make sure you realize it really does equal 10 miles. Did you pause it and do it? Look, you might want to do this vertically. So this is 6 1/4 plus 2 1/2 plus 1 1/4. Remember, you need a common denominator. The common denominator can be 4. So that means 6 1/4 will just stay 6 1/4. But 1/2, I need it as something over 4. I need to multiply by 2 over 2. And that's going to make this 2 2/4. And then 1 1/4, I'm just recopying. Now let's add down. 1 plus 2 is 3 plus 1 is 4/4. 6 plus 2 is 8 plus 1 is 9 4/4. Now, we know 4/4 is equal to 1, so that's 9 plus 1 equals 10 miles, right? Okay? All right. Now, because I'm at the 30-minute mark again, I don't want to make these videos so dreadfully long. I'm going to pop out, and I'm going to make a part 3 for this video that I don't expect to last 30 minutes, but it could, okay? So I hope everything's going well for you. Please, please don't stress over these word problems. We're just working on strategies, trying to be patient about taking in the information, understanding the problem, developing a method, carrying out the plan, and looking back just to make sure it made sense. So always remember that, and then you apply different strategies, and I have several more I want to do for you in part 3 of the video. I hope you have a great day. I'll be back soon.